Hi everyone, Mrs. Hanson here again, beginning a new journey with you today on chapter 15 called The Three-Dimensional Shapes of Molecules. In this chapter, we continue our lessons on stereoisomers. So far, we've explored cis and trans configuration of an alkene, remembering that cis and trans with that double bond is one form of stereoisomers. We had mentioned if we have R groups on that double bond that are on the same side of the plane, that those would be called cis configurations. And another example of a stereoisomer would be in a trans configuration. We explore further some more three-dimensional shapes of molecules in terms of chirality. We'll introduce what chiral centers are, specifically if we have a carbon atom that is attached to four unique atoms or four unique attachments, if you will. How about if I just call those W, X, Y, and Z? That the order of attachment, specifically in the direction, will create a molecule and a unique mirror image. That's what we'll learn about in this chapter known as chirality. We'll look at some applications of these chiral centers in biomolecules as well, specifically an opportunity to look at pharmaceutical applications and the sense of smell applications, and we'll talk about Fisher projections and optical activity. So focusing on the view of biomolecules and organic molecules from chiral centers, those centers that have four unique attachments around a carbon. So in our chapter, we're going to learn how to recognize whether a molecule is chiral or achiral. You'll be able to identify any chiral centers by looking at the carbons and seeing what they're attached to. Do they have four unique attachments? We'll draw two enantiomers, and that's going to be a word we hear over and over, enantiomers, a molecule and its mirror image. Those mirror images to be chiral will be non-superimposable, and we'll spend time showing us what that means. We'll explain why some chiral drugs have very different properties from their mirror images. We'll learn how to draw Fisher projections and compare the physical properties of enantiomers, those non-superimposable mirror images of molecules that are chiral. We'll learn the difference between enantiomers and diastereomers, and we'll be able to explain the relationship between shape and odor of a molecule, going back to that sense of smell. So with our stereochemistry, let's just kind of put it into a frame of something we can think about by looking at your hands. Are you left-handed or right-handed? And it seems if you're right-handed, you've probably spent little time thinking about your hand preference. If you're left-handed, you probably learned at an early age that many objects, such as scissors and baseball gloves, they fit just for the righties in the world, but they're backwards for lefties. Hands, like many objects in the world around us, are mirror images that are not identical. That's what we explore in this chapter, the handedness of molecules. And we ask, why is that important? Why is it important to understand the three-dimensional shape of a molecule and be able to apply that shape in a biomolecule pathway? So our first section, you have your notepad out for chapter 15. We're going to take some notes from a review and kind of bring in some things we know about isomers and then start learning how to build even further. So let's remember isomers. They're different compounds with the same molecular formula. We know that isomers can either be constitutional or stereo. So our first term, isomer. Those share the same molecular formula, but they connect in a different order. Constitutional isomers, we've been practicing since our very first day of class together. Let's practice again just to bring it back as review. Constitutional isomers can have the same functional group or they can have different functional group. Let's draw an example together of two constitutional isomers that have the same functional group. So our molecular formula, C6H14, I'd like to draw two constitutional isomers, which means I'm connecting 6 carbons in just a different order. The first I'd like you to draw would have 5 carbons in the longest carbon chain. And then off of carbon 2, I'd like you to place a methyl group. Draw in your first box the molecule known as 2-methylpentane with the molecular formula C6H14. Notice the methyl group is being branched off of carbon 2. You'll compare that to its constitutional isomer, so in your next drawing, you're still going to repeat those 5 carbons in the longest carbon chain, but you'll make it a 3-methylpentane. Off of carbon 3, you're going to place the methyl branch. In terms of skeletal structures, it's always good to keep practicing that. 1, 2, 3, 4, 5. Carbon 1, carbon 2, carbon 3, carbon 4, and there's carbon 5. If the branch comes off of carbon 2, we have that as 2-methylpentane. If the branch comes off of carbon 3, we know that is 3-methylpentane. They are constitutional isomers that share the same functional group. Constitutional isomers with different functional groups can be modeled with these 2 examples. Ethanol is a 2-carbon chain, and its functional group contains the hydroxyl group. We're learning that the OH in the presence of a molecule creates a functional group known as an alcohol. Remember that those oxygens have lone pairs. We can draw those in as well. So carbon 1, carbon 2, leading out to an alcohol, the skeletal structure of ethanol. A completely different functional group, yet shares the same molecular formula, is an ether. The ether, we know, contains the oxygen directly in the backbone of the molecule. And when I look to the left and look to the right, I see methyl groups there. So we named that dimethyl ether. We practiced these functional groups in chapter 14, those functional groups that contain single bonds to oxygen from the carbon. Now here's 2 constitutional isomers that share the same molecular formula, but they have a different functional group. Let's review and bring into the next focus stereoisomers. These we know are different because they have the same connectivity, all the atoms bonded in the same order, but they have a very different 3-dimensional arrangement. This chapter focuses on stereoisomers, same connectivity but arranged differently in space. They cannot be converted into one another by a simple bond twist. And let's review what that means in terms of our cis-trans isomers. And I like this picture before I go to the next slide, just showing you the handedness of molecules. And so if I think about this carbon in the center here, it's leading out to 4 unique attachments. One of those attachments looks like a hydrogen atom. Here is a carboxylic acid. See that carboxylic acid group? This might be another alkyl chain, and this right here is an amine functional group. Those are 4 unique attachments. So the way that they're bonded to that carbon atom matters. The handedness of a molecule, just like our hands in front of us, are non-superimposable mirror images. That when I pretend, to hold up a mirror here and see the reflection, I can't just simply overlay. Can you use your imagination and just think, what would happen if I just picked up my hand or this molecule and laid it on top of one another? Well, certainly you see that your thumbs don't align, your pinkies don't align. They are mirror images, but they cannot be superimposed. Oftentimes in nature, we see chiral substances, such as this seashell. Notice that it's twisting in a unique way, that I cannot take its mirror image and superimpose it. They spin in a different way. That's our focus, to challenge ourselves to think in a 3-dimensional way. So these stereoisomers differ only in their 3-dimensional arrangement of the atoms. They always have the same functional group. They'll always connect them in the same way. But if their order spins light in a rotation that's opposite from its mirror image, we'll learn to call those chiral. We said stereoisomers are called cis and trans as an example, and we just want to emphasize that stereoisomers, such as cis-trans, are not converted into one another by a spin. So I'm not able to just twist that bond and convert the cis into the trans. That double bonds do not have freedom to rotate. There's a good note to add to your page. So when I want to make a cis turn into a trans, I literally have to break that bond. I literally have to break this bond, and I would have to convert those into the trans by bond breaking, not by bond spinning, because a double bond cannot be, it's rigid. It just can't rotate. These cis and trans are in fixed positions. Let's practice just to bring back a little bit of our earlier knowledge on stereoisomers, constitutional isomers, or identical. What I'd like you to do is just pause the video and stare at these molecules a little bit and make a decision. Are they stereo, constitutional, or indeed identical? Okay, welcome back. Let's take a look at what we found. First thing I like to do is just count the number of carbons and make sure that, in terms of being the same, or isomers, they have to have the same number of carbons. So I'm just going to look at structure A. And another helpful tool is to actually name this compound. Between carbon 3 and 4 is a double bond of a 6-carbon chain. So we call that 3-hexene. I noticed that the double bond between carbon 3 and 4, the group coming off of carbon 3 is pointing down. The group coming off of carbon 4 is pointing up. Just think of this double bond. And notice that they are on opposite sides. So this is called trans 3-hexene. Here I notice that I have a cyclic structure. There's 4 carbons in a cyclic chain, and just to make sure that we still have 6 carbons over there, we have the same number of carbons. They're just arranged in a different order. We would see that this would be called ethyl. 2-carbon chain here is the ethyl group, is the functional group right here. And we would name that cyclobutane. There we got it, ethyl cyclobutane. Clearly, A and B are very different, right? They have the same molecular formula, but they are definitely bonded in a different order. Let's tackle this structure. 6 carbons in a chain. I notice between carbon 3 and 4 is a double bond. So I know that it will be 3-hexene. But what makes it different from the first structure in letter A? The 2 carbons that are in the double bond have their group coming out in the same direction. So this we've learned to call cis 3-hexene. Stereoisomers share the same order of bonding, but they arrange their atoms differently in 3 dimensions. Letter A and letter C are stereoisomers. The cis-trans configuration is an example of stereoisomers. Letter A and B share the same molecular formula, but they are not bonded in the same order, so they are constitutional isomers. And you know what else you could say is B and C are also constitutional isomers. The stereoisomers are the cis-trans configuration. Are you getting comfortable with those decisions? Let's try some more in your packet. I encourage you to pause your video and work ahead. Don't steal your chance of thinking through for yourself. That's really where your learning deepens. Start the video back up when you want to hear me share some thoughts. Okay, let's take a peek if these are identical, constitutional, or stereoisomers. First thing I recommend is naming. 1, 2, 3, 4, 5 carbons in your first structure, At carbon 2 and at carbon 3, I see methyls. So I'm going to label that 2, 3, dimethyl. And then we hear that root word pentane. Let's see what we have in our next structure. I'll pick this side to run. 1, 2, 3, 4, 5. So we have 5 carbons in the longest carbon chain. But look what happened. The attachments are on carbon 2 and on carbon 4. So these have unique names, meaning that they are unique structures. 2, 3 dimethyl, 2, 4 dimethyl pentane means that these are constitutional isomers. They share the same molecular formula, but they have connected them in a different order. All right, let's see what we have in our letter B example. Here I notice the double bond. 1, 2, 3, 4, 5 carbons in that double bond. Between carbon number 2 and 3 is a double bond, so I'm going to hear 2-pentene as its name. And then I notice that it meets the criteria of being a cis configuration. The carbons in the double bond are leading to their alkyl groups in the same direction. So I will have the cis as part of its name, cis-2-pentene. Now when I look at this structure, I can see the same order of bonding. Between carbon 2 and 3 is a double bond of a 5 carbon chain, so you named that 2-pentene. But now I notice that the carbons in the double bond have their alkyl groups coming out in the opposite direction of that plane, so you added the term trans when naming it. Cis and trans are examples of stereoisomers. Let's look at letter C. I have 1, 2, 3, 4, 5 carbons in that chain. I don't have it drawn in terms of a stereoisomer, but I can think about it not meeting the criteria of cis and trans because I have 2 identical groups coming off of the first carbon. So it's impossible to have cis-trans when the carbon in the double bond is attached to 2 like elements, such as hydrogen. So this is simply named as 1-pentene. And as I come down this direction, all I've really done is spun the molecule in the opposite way. Between carbon 1 and 2 is the double bond. Notice that it's still attached to 2 hydrogens, making a cis-trans configuration impossible. So this is also 1-pentene. These molecules have the exact same name, and there is no stereochemistry to consider since it's not possible to be cis or trans. These molecules are exactly the same, so I think we were told to call identical. One more to check with me. Notice here I have an oxygen in a cyclic structure. I know that that is a functional group known as an ether. I have 1, 2, 3 carbons. I have 1, 2, 3, 4, 5, 6 hydrogens and an oxygen, making that ether in a 4-membered ring. Here I have a 3-membered ring with an alcohol functional group. 1, 2, 3 carbons, just like our first model. There's 1, 2, 3, 4, 5, 6 hydrogens and the oxygen. Well, look at that. They share the same molecular formula, they're bonded in a different order, and they have completely different functional groups. That meets all the criteria for a constitutional isomer. Same molecular formula, different connectivity. I bet you're doing great. Let's consider the trans-2-hexene. So it says, let's just think about what that means. Here's trans-2-hexene. So between carbon 2 and 3 of a 6-carbon chain, we have a double bond. To be trans, one carbon will have to come up above the plane of the double bond, and the next carbon would have to come down out of the plane. And then, of course, we would just zigzag for carbon 5 and carbon 6. So that's kind of what we're looking at for the structure of trans 2-hexene. Let's draw a stereoisomer. Well, the stereoisomer of a trans is a cis configuration. So what we're really being asked is simply show both of those alkyl groups coming out of the double bond pointing in the same direction. So the stereoisomer still places the carbon 2 and 3 double bond, but instead of having one come up and one go down from the plane of the double bond, they both will go up or both go down. It doesn't matter. They just have to be on the same side. So carbon 1, 2, 3, 4, 5, 6. So in terms of your configuration, carbon 1, 2, 3, 4, 5, 6, this is a trans. Notice that that trans follows the zigzag, the two carbons in the double bond. One is coming up, the other coming down. That's the trans configuration. Now, when I think about the cis and how the bond line has to work there, in order for both to come up out of the plane, the double bond, I always like to start with that position of the skeletal structure. Carbon 1 is pointing up, carbon 3 is pointing up to number 4, and then I can just continue my zigzag. 1, 2, 3, 4, 5, 6. There's my cis configuration. Alrighty. So that tells me, just to remember the ene general formula, remember that was CnH2n. So we had 6 carbons and 12 hydrogens. That's what we were allowed to build those. Okay. Now in letter B, it says draw a constitutional isomer that contains a carbon-to-carbon double bond. Well, what that tells us is that to be constitutional isomers, we have to have them bonded in a different order. So we really between two different carbons. So instead of between carbon 2 and 3, we could make it between carbon 1 and 2 and see how that works for us. Carbon 1 to 2, double bond, and then 3, 4, 5, 6. If it's the first configuration, 1, 2, 3, 4, 5, 6, notice if it's between carbon 1 and 2, there is no such thing or cis or trans because we have 2 hydrogens coming off of carbon 1 to complete its 4 bond requirement. There's 2 hydrogens coming off of that terminal carbon, and since they are identical atoms, it's not possible to have cis-trans configuration. But that's absolutely okay because we're just asked to draw a constitutional isomer. This meets that criteria. 1-hexene is a constitutional isomer of the trans or cis 2-hexene. What if we had drawn a 6-carbon chain and put the double bond between carbon 3 and 4? Would that also have been a good choice? And the answer is absolutely, because they are not connected in the same order. This is another constitutional isomer. It has its own unique name. We know that this would be called 3-hexene, and this has the possibility of being cis or trans because the double bonds are connected to different atoms. So, for instance, here's carbon 3 and 4. In a cis configuration, we would have 2 carbons on either end coming in the same plane heading up. So this would be the example of cis 3-hexene. Or we could have those coming down in the opposite directions of that plane of the double bond. And this, of course, would be called our trans 3-hexene. So this actually had multiple correct answers, multiple ways to address that question. And so I just wanted to make sure that since you worked ahead, you wanted to know if your answer was correct. I wanted to show some possibilities. Of course, there's our double bond. There's carbon. Just thinking about 1, 2, 3, 4, 5, 6. That would be trans configuration for 3-hexene. You might see it 1, 2, 3, 4, 5, 6. Same thing. Alrighty, those are identical drawings. With your cis configuration, we had the double bond between carbon 3 and 4. So it comes up. Well, I'll draw it like this. Here's our cis configuration. Between carbon 3 and 4, we see the double bond. So practicing both with connectivity with line structure and kind of that condensed formula. Okay, good. Let's see a little bit more on this page. It said letter C, draw a constitutional isomer that does not contain a double bond. Now that one, we really want you to think about no double bond, but we have a CnH2n formula. Right, because that's our general formula for the alkenes that contain a double bond. Do you remember what else matched that same general formula? Well, not only does the enes represent CnH2n, we remember learning that CnH2n is the general formula for a cycloalkane. So if I had to have 6 carbons in a cyclic structure, and I could just kind of think about those 2 carbons in a row, you know, if I had a straight chain of 6 carbons, I'd have to remove carbons at the end in order to attach them in a cyclic structure. So a cycloalkane is also CnH2n. So cyclohexane, all single bonds in there, would have the same shared formula of C6H12. Just as we had for the 1-hexene, this is C6H12. We could not have a straight chain alkane. The straight chain alkane has the general formula of CnH2n plus 2. We need those 2 carbons at the end of the terminal chain to finish the 4 bond requirements of the terminal N. So this would not work. We needed a cyclic structure to make that work. All right, you've done great work. Let's look at a next section together and start considering stereoisomers and their mirror images. And this is a little snapshot I took from your book. To learn more about stereoisomers and tetrahedral carbons, we turn our attention to molecules with mirror images. These are 2 identical twins. They're named Zachary and Matthew. Obviously, I've never met them. That's clip art from your text. One of these twins is left-handed and the other is right-handed. In nature, we often see mirror images that are non-superimposable, and we'll learn to call those chiral molecules. Looking in a mirror, they seem pretty identical, and yet they have a unique handedness, making it chiral. Molecules and their mirror images, what it means to be chiral or achiral. Hold your hands out in front of you and just examine them. You have a left hand where the thumb points to the left direction when the palm is up. You have a right hand where your thumb points in the right direction when your palm is up. If you take your hands and overlay them so that palms are up, your thumbs are on opposite sides. When you hold them to a mirror, they reflect in the same manner. You get a mirror image, and yet when you overlay them, they're very different. These are great examples of chiral objects. Left hands and right hands are mirror images, and yet they are non-superimposable. I cannot get a glove that's made for my left hand to go onto my right hand and fit well. Molecules exhibit the same center. If I have a carbon atom with 4 unique attachments, the way that I bond those atoms onto the carbon makes them the same or a mirror image. Notice that if I put a mirror here, it's reflecting back perfectly. The mirror image is just like the hand in the mirror. And yet, if I take this molecule and place it right on top, they do not overlap perfectly. This R group would be on this side where the hydrogen is. The hydrogen becomes on this side. So you can see they possess the same four attachments, but they're not connected in the same spatial order. So that's what I'm trying to write here, is bonded in a different spatial arrangement to make them unique. So just think about in terms of spinning. Let's just call, kind of thinking about order of priority. I'm going to just call this molecule, the COOH, 1. Let's call this R, whatever R might be, functional group 2. And let's just call this amine, functional group 3. And when I spin in clockwise or counterclockwise to attach those, notice that the priority in which I just labeled those has a clockwise spin in the first molecule. The same attachments on the other molecule spin in the counterclockwise fashion. So that's what I'm telling you, that was supposed to say spin, clockwise spin, and a counterclockwise spin. They're spinning in opposite directions. And so when I'm thinking about, are they the same or are they different, I usually will just decide the attachment of the molecules, those R groups, these things that are attached to the central carbon, assign them a priority. Just, I randomly say COOH, you're going to be number 1. The R group, I'll call you number 2. The amine group, I'm going to call you number 3, just to keep them in order in the track. Now, when I spin, I just connect the numbers. And if I'm going in this direction, that's the order of a clock, clockwise spin. And if I'm going in this direction, that's the counterclockwise spin. Therefore, I now know these molecules are different. They are not the same molecule because their attachments are spinning in an opposite direction. Left and right hands are not identical. We had said they're non-superimposable images. This is an example of a chiral object, a molecule that's not superimposable on its mirror image. So if you think about just overlaying your hands, the thumbs don't line up, your pinkies don't line up. Example of a chiral object, a non-superimposable mirror image. And yet, a sock, for example. Does it matter which foot you put your sock on? Well, not at all. They are said to be achiral because they are superimposable mirror images. There's no difference between your left and your right sock. There is no such thing as a left and a right sock. But it's not true for a glove. Gloves are a chiral object. Socks are an achiral object. Notice that a sock can easily be overlaid on its partner, and therefore, since there's no unique attachment, they're said to be achiral. So let's examine just some ordinary objects and decide, are these objects that are chiral or achiral? Is there something in a unique attachment that would make it spin light in a unique way? Well, the first one is a set of nails, it looks like. And clearly there's nothing on this nail that would not allow me to just overlay one object onto the other. Since there's nothing unique about that object in terms of attachment, that is an achiral object. They are superimposable mirror images. They lay on top of each other exactly the same way. The next example is a screw. You know that a screw has an inclined plane wrapped around that. So notice that the order of twisting here is kind of leading up with this inclined plane. Its mirror image would not be superimposable simply because it would have this inclined plane, this wrapped around twisted part of the screw, going in the opposite direction. This is a chiral object. It has a non-superimposable mirror image. The next one is a glove, and as we said already, hands, just like a glove, is a chiral object. It has a non-superimposable mirror image. They are unique. A left glove does not fit on your right hand. And a pencil is an achiral object. There's nothing unique attached to that pencil that would cause it to have, one pencil could just simply overlay on the next. There's nothing unique to prevent that. The reason the screw is because of the direction of the inclined plane going around the screw, because it could actually have an opposite feel to it. Now, it's hard for me to draw, I understand, but if the screw goes in the left direction, it would have an opposite direction going in, spinning the opposite way. So that one was kind of the visual there that I'm trying to draw for you. So the test of chirality, to determine whether a molecule is chiral or not, we have to really think about it in 3 dimensions. So we start by drawing the molecule in 3 dimensions. We then draw its mirror image to try to align all the bonds and atoms. To superimpose a molecule with its mirror image, you can perform any rotations. You can spin the molecule, but you're not allowed to break bonds. So when we test the chirality of a molecule and look for chiral centers, we're trying to find carbons that have 4 unique attachments. And remember, as we draw those, carbon has 2 of the 4 bonds in the same plane. One of them will come out of the paper as a wedge, and the 4th goes behind the paper as a dash. We draw its mirror image and decide, do these line up to be the same, or are they different by the way they're bonded to the carbon? You can twist them, but you cannot break bonds. Let's go through some examples of molecules. For instance, let's draw a water molecule. Notice that the oxygen, and you could literally draw the Lewis dots with me. You don't have to draw the ball and stick. The oxygen is up top, and we have 2 hydrogens coming down. The oxygen has 2 lone pairs. Its mirror image, place a mirror and see what you find, provides the exact same object. This oxygen, it has 4 electron domains, 4 attachments, but remember, 2 of those domains are lone pairs. 2 of them lead to atoms. So remember the VSEPR, the valence shell molecular geometry. 422 gives me a bent molecule. So just thinking about molecular geometry, remember, to meet the criteria of being chiral, to say that you're chiral, you have to have 4 domains that are different. And I'm going to say attachments because we can see in a moment that those attachments, we're going to expand what that idea is. Since this oxygen is not even leading to 4 other atoms, and I see right away that 2 of the atoms are the same, right away I know that this is not going to be a chiral molecule. It does not meet the criteria of 4 unique attachments around that central atom. 2 of them are identical, hydrogens, and 2 of them don't even lead to atoms, they lead to lone pair electrons. Water is an example of an achiral molecule. It has a superimposable mirror image. They are identical in 3 dimensions. A next example has CH2BrCl. Now I'm going to draw that with you on your paper. Let's make the hydrogens in the same plane. Alrighty, so I can see that's what's happening here. Those hydrogens are in the same plane. The bromine is coming out at you, so that's a wedge. And this chlorine, which is green, we're going to make that the dash. It's going behind the paper. All right, so there's my first ball and stick model there, using dashes and wedges to show a bromine, chlorine attached to a carbon. When I draw its mirror image, the hydrogen still comes up. The hydrogen is still in the same plane, but on the opposite side. And see how chlorine now is up here and bromine down here. That's the mirror image. So that's me trying to draw what they have in a ball and stick model. Now, clearly, I can rotate the molecule. I'm not breaking bonds, but I'm rotating the molecule. And now I notice that I can create a superimposable mirror image. They are identical. They lay right on top of each other and line up. So this is an achiral molecule. Achiral. Now, here's how I knew that immediately. Do you notice that two of the attachments are exactly the same? There are not 4 unique attachments on that carbon. Right away, I can see that it does not meet the criteria of being a chiral carbon. To be chiral, it must have 4 unique attachments. So as soon as I notice 2 are the same, it won't be chiral. What about 4 unique attachments? And I have these on your notepad. I have them in color. Maybe you're printing in black and white, but clearly you can see there's 4 different attachments. Let's draw this together in structure A. I'm going to do the same thing on my paper here. So the carbon in the center, there's a hydrogen going up, and the chlorine is in the same page, the same plane. That's the green, that's the chlorine. This is bromine, and this one is fluorine. So there's the 4 unique attachments. Notice bromine is coming out of the page, so I make that the wedge. And I'm going to make fluorine the dash because it's going behind the page. Let's place a mirror here and draw what we see. Reflection. Hydrogen still going up. Fluorine now is reflecting to this side. The bromine is reflecting to this side. And the chlorine in the same plane over here. Now, let's assign priorities, if you will. Let's do that by saying, since bromine is the largest atom, for no other reason, I'm just needing to assign problem. Let's call bromine 1. So I'm going to number that. Bromine is number 1. Chlorine is number 2. Does not matter what I call them. I just want to know what I'm keeping track of. Bromine, chlorine. Let's make fluorine number 3. Are they spinning the same or spinning in opposite directions? Connect your numbers. Our first is spinning in a clockwise fashion. So leading from bromine to chlorine to fluorine gives me a clockwise spin. Bromine to chlorine to fluorine in this next mirror image is giving me a counterclockwise spin. They're spinning in opposite directions. Therefore, they are not attached in the same spatial arrangement. No matter how I twist and turn molecule A and B, they are not superimposable. They do not line up. Therefore, this is finally an example of a chiral carbon. This molecule is chiral. That carbon has 4 unique attachments. Its mirror image is non-superimposable, and I'm proving that by the spin of the molecules. When we align them, they don't match up. So that's really what we're looking at to figure out if something is a chiral center. Does it have 4 unique attachments? And if so, its mirror image would be non-superimposable. When I looked at carbon attached to hydrogen, attached to bromine, chlorine, and fluorine. 4 unique attachments. So what I'm saying is hydrogen is very different than fluorine, which is very different than chlorine, which is very different than bromine. 4 unique attachments created a chiral carbon, a chiral center in that molecule. So if you have 4 different groups, you are making what's known as a chiral center. Molecules can contain 0, which we would know as achiral. They can have 1 chiral center, or they can have many chiral centers. It just looks at how many unique attachments that carbon has. And to locate these chiral centers, we examine carbons with 4 different bonds. So we're going to look at each tetrahedral atom, specifically the carbons in organic molecules, to find carbon centers that are chiral. Look at the 4 groups, not the 4 atoms, but the 4 groups. And I want to emphasize that with the next example, bottom of page 3 if you've printed there. Now here's an example, and I can clearly see that the carbon in the center is attached to an iodine, which is different than a fluorine, which is different than a chlorine, which is different than a bromine. This meets the criteria of being a chiral center, 4 unique attachments. So that if I consider, in terms of drawing it in a dash wedge, if we put bromine in the same plane, and I'll put chlorine in the same plane, I'll make fluorine come out and iodine go back. Its mirror image would have bromine up top, chlorine off to the right now in the same plane, fluorine down here, and the iodine up here. That's its mirror image reflecting back. So just pretend there's a mirror here and draw what you would see for its reflection. The test of chirality: assign priorities. Let's just call bromine 1. I'll call chlorine 2. I'll call fluorine 3. And I'll just leave the iodine off. I only need to spin 3. When I connect in order of 1, 2, 3, this is spinning counterclockwise. How about that? CCW, counterclockwise. And when I connect these 3 attachments, I can see that it's a clockwise spin. Therefore, these are non-superimposable mirror images. And that's our very definition of a chiral center. But I want to expand that in terms of what makes an attachment unique. So I have to consider all the atoms in a group as a whole unit. So for instance, here's a carbon that's attached to 4 items, 4 groups. When I first consider, let me just highlight, I can clearly see the hydrogen is very different than the bromine. Those are 2 easy ones to pick out, so 2 unique attachments there. But notice when I lead out to the first carbon, I might be fooled into thinking, oh, they're the same. The first link out from that central carbon is identical. It leads to another carbon. But keep going until you see if there's a point of difference. I'll go next and I still lead out to another carbon. So no point of difference yet. However, what about if I go just one further? This guy is a point of difference between that central carbon. This in terms of an alkyl group would be called propyl, and this in terms of an alkyl group would be called ethyl. Ethyl is not the same as a propyl, so they are indeed different alkyl groups. This does meet the chirality center criteria. 4 unique attachments, looking at the unit as a whole unit. Don't just pause and look at the first atom to make your decision. See if there is a point of difference between those attachments. Let's model one and just kind of expand that. Instead of if we had H, I'll put a Cl. And if I had this molecule, this is just simply a 5-carbon chain at carbon 3, there's a chlorine. So we would call that 3-chloropentane. Is that chiral or achiral? Well, I'm going to focus the attention here on this carbon because I can see it has a chlorine coming off of it, and I know hydrogen is different than chlorine, so that's 2 unique attachments. I'll look then in the left direction, and they both lead to carbons, so there's no point of difference. I'll go 1 atom further, still no point of difference. These 2 groups are identical. In terms of an alkyl group, this would be 2 carbons. In terms of an alkyl group, this would also be 2 carbons. And since they are identical, there's no point of difference from that middle carbon. I look this direction, it's the same as looking this direction. So this would qualify as an achiral object. Carbon number 3 is achiral. I must have 4 unique attachments. So a carbon atom that's bonded to 2 or more like groups is never a carbon center. CH2 and CH3 groups have more than 1 hydrogen atom bonded to the same carbon, so they're never chiral centers. So what that's saying is if I have this carbon chain and I have a CH2, CH2, see how I'm just leading? These will never be, because there's 2 hydrogens, that's identical, never a chiral carbon. And if you're at the terminal end of a chain, notice that there's 3 hydrogens, that's never going to be a chiral carbon. We must have 4 unique attachments. And you know what that also means? If you have a multiple bond, what I mean here is like carbon to carbon, that will never be chiral because it's leading to the same atom twice. So never a chiral molecule. Even if it's a triple bond, you can see that that would never be chiral. So we're looking for 4 single bonds around a carbon atom that leads to 4 unique groups. That will create a chiral center. These chiral centers and examples are labeled in red. So let's examine this first carbon. Does it have 4 unique attachments? Well, the first carbon, I'm examining, just remember this first carbon right here, it's leading to a hydrogen, and it's leading to a hydroxyl, and it's leading to a COOH, and it's leading to a carbon. Those are 4 unique attachments. Now I know that you're saying, this is also a carbon, and this is a carbon, but this carbon is attached to OOH. And since there is a carbon between the COOH on the right-hand side, those are 4 unique attachments. So think about carbon 1. Here's carbon 1. What is the 4 attachments? One of them is an H, one of them is an OH, one of them is Cu, and the other is a carbon and then a Cu. Those are 4 unique attachments. And this will have the identical, that is also a chiral carbon. And just looking at why, because it has 4 unique attachments as well. I'll call this carbon 2, C2. Notice that it's attached to an H, it's attached to an OH, it's directly attached to a Cu, and it's attached to a carbon Cu, and those are not the same. So they have 4 unique attachments. We're looking at chiral centers. So that's the test. It's as easy as can be once we get practicing. Here's a carbon attached to a hydrogen, which is different than an OH, which is different to a benzene ring. That's all the same attachment. And then the 4th group would show a C bonded to an NHCH3. Carbon number 1 is attached to 4 unique groups. And so is carbon 2. This carbon is attached to an H, a methyl, an NHC, and then a carbon leading to a benzene ring. That's ephedrine, which is a bronchodilator, decongestant, Tartaric acid contains 2 chiral centers as well. So I'm going to encourage you to practice. You've got a page there, page number 4. Perhaps you want to gather a highlighter and test. Do you find any chiral carbons? Highlight those and come back to check with me when ready. Again, don't cheat yourself of the practice. Page 4, work them out, come back when ready to check. Identify the chiral centers. Well, let's see what we can find together. So I'm going to just take a highlighter and I'm going to examine each carbon. First of all, this carbon here, let me just number them so we can find those. Carbon number 1 contains a multiple bond, so that is no. So when I see a multiple bond, like a double bond, I can automatically exclude that one. Not a chiral carbon. How about carbon 2? Well, that looks interesting. Let's give it the test. Carbon 2 is leading to a COOH. It's leading to a hydrogen. It's leading to an amine. And it's leading to a carbon attached to some other things, right? So all that is unique. This guy is indeed chiral. Carbon 2 has 4 unique attachments. What about carbon 3? With carbon 3, I can see that, oh, look at this. I have 2 attachments that are the same, so that's not chiral. So I eliminated that choice. The only one that came out chiral was carbon number 2, and I'll highlight that in blue. 4 unique attachments. How about letter B, albuterol? What did you find there? Well, I can just kind of begin looking around and notice that anytime I have carbons in a multiple bond, such as this aromatic ring, I'm not even going to examine them. Here's a carbon, but I see it's attached to 2 hydrogens, so I'm not going to examine that. It doesn't have 4 unique attachments. Anytime I see a CH2, there's 2 hydrogens on that carbon, it doesn't meet the criteria. Let's examine this carbon. And I'm going to just put a little box around it maybe. Highlight what we see. I have an attachment of an OH, which is different than an H, which is different in this direction, as it is different in this direction. That is a chiral center. So I hope you found this one as well. The other example, just to kind of consider, is here's a carbon right here, but keep in mind it's attached to 3 methyl groups, and then it leads to that nitrogen. So clearly seeing 3 units of a methyl group eliminates that one, so that's a no, that is not chiral. So in letter B, the only chiral center you found, why don't we highlight here and that central carbon? Cool, how you doing? Here we have letter A, and in this example, if I just kind of look at drawing out, I have a carbon attached to a hydrogen, chlorine, a methyl group, and then an ethyl group. So I do see 4 unique attachments. This carbon is a chiral center. It's attached to a methyl group, CH3. It's attached to a hydrogen, attached to a chlorine, and there is a point of difference because an ethyl is not the same as the methyl around that central carbon. So there is 1 chiral center. Letter B has a carbon attached to a hydrogen, and the other 3 bonds lead all out to the same group, to methyl groups. I find nothing unique around that central carbon. This is an achiral molecule, no chiral carbons at all. Let's see here. Well, letter C looks interesting. If I take that C to C double bond, I eliminate those choices. Here's a carbon attached to a hydroxyl and leading out to a methyl. So see what we've got here. Just kind of drawing out what letter C looks like to see the attachments in all bonds. I can notice that this carbon has a hydroxyl attached, a hydrogen attached, a methyl attached, which is again different than this part of the alkyl chain. So we do have a chiral carbon right here, 4 unique attachments. And I can see this guy right away. This carbon right here will end up being chiral because I can see a methyl, bromine, hydrogen, and an aromatic benzene ring, 4 unique attachments, 1 chiral center. You're getting better, I know. We can eliminate choices very quickly if they don't meet the criteria. So all of the CH3, CH2, I see this guy right there. He is a chiral center, 1 carbon out of that whole carbon chain that has 4 unique attachments. Now, we haven't seen these yet, but we're going to. These are what we're going to learn to call as Fisher projections. Just throwing this out now. We'll come back to it a little later in the lesson. But notice I have a carbon chain kind of leading up and down in the same plane. We'll learn what that means in a second. But right now, I'm just looking at attachments. How about this carbon? So let's see what we have. That carbon is leading to a Cu, leading to a hydrogen, leading to an amine, and then leading to a longer carbon chain. So those are indeed different. That is a chiral center. That meets the criteria. So yes, this carbon, and I'll just leave them highlighted, that's chiral. What about the one underneath it? It is as well, isn't it? This chiral center has 4 unique attachments. And if I just think about it, hydrogen, methyl, ethyl, and a carbon leading up to a Cu and attached to a nitrogen, 4 unique attachments. There are 2 chiral centers in letter B. How about what's happening here in letter C? Well, I can eliminate CH3, CH2. Let's examine this carbon, see what's going on there. I can tell that a bromine is different than a hydrogen. I'm examining this carbon, and I can see that an ethyl group is in this direction, and clearly you can see that this is very different in the right side, right? So this group is unique from the left group. So indeed, that carbon with all the color around it is chiral. So with that, we found 1. 4 unique attachments. I'll just highlight in blue. This guy is chiral. How about the other one? Let me just highlight this. Does this meet the chiral test as well? And certainly it does, because a methyl group in one direction, we have a chloro in the other, hydrogen down here, and this entire chain makes that a 4th unique attachment. So this had 2 chiral centers. The chirality in letter C coming from 4 unique attachments, highlighted in blue and in green. You've got some more over on this side. When I draw out the structure of letter A, I can see a 1, 2, 3 carbon chain. I'll probably have to number it from the opposite direction. 1, 2, 3 carbon chain. Carbon 1 has 2 chlorines and a hydrogen. I don't find any chiral. That is nothing going on in there. Achiral. Let's see what else we have. Letter B, if I examine this carbon, that carbon is leading to 2 identical groups. So that is not chiral. But how about this guy? What about this carbon? Right, kind of consider the attachment. You have a 1, 2, 3, 4, 5 carbon chain. Carbon 4 has a chlorine. Carbon 2 has a methyl. That means there's a hydrogen here. Hydrogen here. We might actually find a couple here. Is this chiral? Oh, no, it's not. How come? Well, these guys are the same, aren't they? Here's a methyl group, here's a methyl group. This carbon is attached to two identical groups. It will not be chiral. All right, so that's fine. How about what I'll highlight now is this guy. So does that meet the criteria? This guy here. He's attached to a chlorine, a methyl, a hydrogen, and a whole lot of other stuff over here. Oh, those are 4 unique attachments. We did find one chiral center. And I'll leave that highlighted right there as the chiral center. Ooh, we have a cyclopentene structure. Let's examine this carbon. So in terms of a cyclic structure, the carbon I highlighted, what is it attached to? So in terms of a group, let's highlight them. We have a methyl, and notice we have 1, 2, 3 carbons before I hit the double bond. And in this direction, I have just 1 carbon before I hit the double bond. And don't forget that even though we don't see it, there's a hydrogen there. We have a methyl, colored in pink, a 1 carbon unit before a double bond, a 3 carbon unit before the double bond, and a hydrogen. Those are indeed different structures. So this guy right here is a chiral center. Now let's try a different approach here where the double bond now is directly attached to that carbon. And we already said that when it's double bonded, it will never meet the criteria of having a chiral center. None of the carbons in there can be chiral because they all have a hydrogen, leading to 2 hydrogens. Carbons that are in double bonds will never be chiral. And of course, this terminal has 3 hydrogens there, so there's nothing happening there. This is an achiral molecule. Beautiful. So great work checking out that in terms of recognizing chiral centers. And what I'll do now is just kind of examine time. We're over an hour, so I'm going to pause the video here and ask you to kind of process chirality. And when you come back, we're going to pick up drawing enantiomers, how to draw mirror images of a chiral molecule.